So this topic is bit relevant now because as you see that there is a lot of trust on automotive application, especially on the transportation electrification side. And induction motors are widely used for Indian railways and different railway systems. So I think this will be a relevant topic. And today we'll first talk about the introductory portion, a bit background of induction motors, and then we'll talk about the scalar control techniques in induction motor drives, followed by the vector control technique. Then, if you are using it for vehicle purpose, then the induction motor needs to operate over a wide speed range of operation. So, corresponding to that, we will talk about the field weakening control strategy, followed by the efficiency optimized control, and then we will try to summarize the overall lecture. So, let us start with the basic introduction. We have in our homes and also in different applications like water pumping systems, and so we have different centrifugal pumps which are there. So centrifugal pumps typically they take the help of induction motor drives. Also, if you see electric traction, the present generation Indian locomotives, you will see there is a lot of use of induction motor systems, right? So, as well as in conveyor belts, as well as in lathe machines, and even in our household, majority of the devices are built on in majority of the motors which are used, electric motors which are used, are based on induction motor systems. Okay, so that's why this topic is relevant, and we took this portion. So the electric traction drive system, if you talk about, like here, this is a single phase system. You take power from the single phase supply, and then it is rectified. And after rectification, it is then again use a variable frequency drive, okay, VFD, to control the speed and torque of the motor. So now, if we talk about the electric powertrain of a battery electric vehicle, if we try to see the different components of the battery electric vehicle, then one of the major components in the battery electric vehicle is the battery itself. Okay, so and it forms the major cost of the battery. But after that, followed by that, there is another important component which is basically used for the propulsion as well as for the braking purpose, that is the motor. Okay, so the motor actually performs the two aspects, like motor have two aspects. That is, one, it can be used for your propulsion or forward movement, as well as it is used for the braking purpose. So these two are the different utilities of the motor. And if you try to see if you try to observe the placement of the motor is placed in this position, right? So corresponding to this position, you have the this is for after that you will have the gear mechanism which will transfer the power from the motor to the mechanical systems, which is finally to the wheels. Okay. So if you try to see the direction of the power flow in case of the motoring system, then you have the battery, then you have the power converter, then you have the motor, and then finally to the wheels. So this is corresponding to the motoring mode of operation. This is the direction of the power flow. Corresponding to the braking mode of operation, the power flow is reversed. It comes from the wheels, then to the motor, to the transmission system, then power converter, and then back to the battery. So the braking system, if there is a regenerative braking system available, then the regenerative braking system can also help in actually the braking of the motor regenerative braking system can actually help in braking, and it will transfer some portion of the power to the back to the battery. So in that way, it can help to replenish some portion of the energy which has been consumed during the motoring mode. It will be again taken back to the battery system. Okay. So now, this is the basic overall application areas where the induction motor is used. Now, when we talk about the control techniques, first of all, we need to develop a mathematical model or a model, an analytical model of the system, such that we can actually apply our control techniques to this. So before going to the control technique, first of all, we will try to recapitulate the induction machine characteristics. Okay, especially basically the speed control is nothing but shifting the torque speed characteristics of the induction machine. So now let us talk about the torque speed characteristics of an induction machine. Or first of all, we'll talk about the equivalent circuit of induction machine. Now here we have the supply voltage or the stator voltage, right? And we will talk about the squirrel cage induction machines in as of now. So you have the stator resistance, right? You have the inductance. Then uh, here there are resistance. This is a rotor resistance. This is the leakage reactance of the rotor, and this is the magnetizing inductance. Vs refers to the stator voltage, which is applied on the on your induction machine, and then corresponding to this, we can actually give a equivalent Thevenin equivalent circuit. The Thevenin equivalent can be obtained by looking through this terminal. Okay, so by looking through this terminal, we can obtain a Thevenin equivalent corresponding to this. Okay, so corresponding to the Thevenin equivalent, we will have this will be the uh, this will be the circuit. So this is a Vs Thevenin, which you can obtain by using this relationship. Okay, and the Thevenin impedance is provided by this relationship. Right. So now we have also the definition of one important term that is called synchronous speed. Now, synchronous speed is defined as 120 fs by p, which is the speed of the rotating magnetic field. And then also we can define slip. Okay, slip is the difference, or slip speed is the difference between the rotating magnetic field and the your rotor's physical rotor speed. So that slip speed is given by omega e minus omega r, or it is the difference between the synchronous speed and the rotor speed. In either it is in radians per second, or it is in rs minus nr, that is in synchronous speed in rpm, right? So this has also been mentioned here. Okay, so these are the different terminologies which will be used. So before going into that detailed mathematical model, so I thought of defining the terminologies before going. So these equations are corresponding to, or the basically we are now trying to define the different terminologies. Right? Okay. So the rotor current. Okay. Now there is corresponding to this equivalent circuit, we can actually derive the rotor current equation, which is given by this formula, right?
Excuse me, sir.
Yes, yes,
Uh,
please.
Sir, what is the significance of like Why we are looking at that point to find out VTH? Because the circuit is already there. So why we are finding equivalent circuit? Because any
Ah, see, we need to find out the torque. To find out torque, we need to know the rotor current. Okay. We need to
okay,
know the rotor current. So how to find out the rotor current? This is given by this expression. And then if you see
okay,
torque expression, the torque expression is given by the rotor, where the rotor current is actually involved. Okay, so this is IR square into RR dash by S into omega S. Okay, so the torque expression is given by this relationship. Okay, so and here what will happen if S tends to zero? Okay, if you see S tends to zero, then this equation will be this portion will become very, very high as compared to the other portion, and finally, okay, so this will become a uh, or it will become like a straight line. Okay, then it can be actually related to that of a, or it can be written that torque is directly proportional to slip, and torque is directly proportional to slip, and at slip equal to zero, voltage induced is zero, and therefore the torque output or the rotor current is also zero. That you can find out from this expression as well. You just substitute S equal to zero, then you will see that the torque output will also become zero. Okay, so that also you can directly obtain from here. And if S tends to 1 or at starting, okay, so if S tends to 1, then you will see that by approximately the torque expression can be written as here, and the torque is inversely proportional to 1 by S, okay, or inversely proportional to S. So that means the torque will have a parabolic nature. Okay, so in this part it is parabolic, and when it is close to 0, it is having a linear nature. So this will be the nature of the torque speed characteristics, right? So, and then we can find out the slip at maximum torque. Okay, so slip at maximum torque will be given by this expression. Okay, and if you see the air gap power and this corresponding to this expression, you can find out that there's a slip at maximum. This is also a utility of the equivalent circuit, that if you want to find out the slip at maximum torque, you equate the variable resistance with that of the internal impedance, and that will be given by RR dash by SMT will be equal to this over under root of this expression. So this is a complete internal impedance, and this will be RR. So SMT will be RR dash by this one. Okay. So this is a torque speed characteristics which is corresponding to a particular voltage and particular frequency. You will get a particular torque versus speed profile for the induction motor. Okay. And then what will be the operating point of this? If you see that if there is a low torque, okay, that means you have this induction motor. What I mean to say, you have an induction motor. Okay. So it is trying to drive a load. Okay, it is producing a torque. So suppose it is producing a torque. It is producing a torque in this direction, and there is a load torque which is in the reverse direction. Right? There is a load torque in the reverse direction. It is given by TL. Now this this is the electromagnetic torque which is developed by the motor, and then you have a counter rotating torque which is given by this expression. This is this is a load torque, and that is a constant irrespective of the speed. It is constant. So what will be the operating point? The operating point will lie on the plane on the intersection point between these two. Okay, and the maximum value of the torque will be given by this expression. And at steady state, it can be seen that T and TL will be equal. So this will be the operating point. Now suppose here what is the speed? Here the torque output is suppose 6 Newton meter and the speed is around 1400 RPM. Right. Now we want the torque to be same. We want that I want to operate at instead of this point, I would like to operate not here, but I don't want to operate here. I would like to operate at this point. Okay, or maybe take a whole number. I don't want to operate here. I would like to operate at this point. Okay, I would like to operate at 500 RPM and get the same torque. So this torque speed characteristics is not possible. Why? This torque speed characteristic because there is no intersection. If there is no intersection, then it is not a basically a feasible operating point, right? So now what I have to do, I have to shift the torque speed characteristics or alter the torque speed characteristics such that my mean I am able to achieve the control here. Okay. So, or I am able to achieve the required torque and the speed. So that is the whole system of speed control. Okay. Or that is what, and I want irrespective of the load torque change, I would like to keep it fixed here. So now we will talk about the different aspects or different techniques how to achieve this. That is the main problem, or that this is the complete background of the story, that how what is required. Okay, so irrespective of the torque, I want to have certain speed. Okay, and that cannot be achieved by a fixed voltage or fixed frequency. I need to shift. You need to change something. Change what? Change voltage or frequency. Okay. The rest of the thing is that how to do it. Okay. So how to do the speed control. Now, what are the variables in my hand? Like we go for voltage control, we go for frequency control, we go for voltage and frequency control, all these things. Okay. Now, if we see the this voltage control, yeah, voltage control is also possible. Like you control the voltage, and instead of this, if you control the voltage, then we'll see this one. See, if we see the torque as expression, then if we see the torque expression, you see the voltage is one of the factor. Then frequency will change the synchronous speed. So if you change the synchronous speed, definitely it will shift from one. If you change the frequency, the synchronous speed will shift, and you can change the torque speed characteristics. Okay. And you can change both. You can change voltage, you can change frequency. Okay. So now you will let us take one variable at a time. Okay, one by one variable at a time, and then we can actually see what are the different aspects. Now, let us go ahead with the different control techniques. Okay, so first of all, we will talk about the stator voltage control. Okay, so if we talk about the stator voltage control, see the stator voltage in the torque equation, it is actually in square, or the torque is actually proportional to the square. Torque is actually proportional to Vs Thevenin square, right? So corresponding to this, we will have, right? So corresponding to this, we will see that the maximum torque will also reduce in square proportion. That means what? If the voltage is reduced by half, the torque will reduce by 1/4. Okay, that is what is meant by square, right? Square proportion. Right, the torque will also reduce by 1/4. Right. So corresponding to this, you have this. This is the maximum torque expression. The maximum torque will also decay, and this will be the correspondingly different This will be the different uh, torque speed characteristic. Now, this, if we try to see, if we see a fan type of load where the torque versus speed is actually proportional to the square, then, or in pump type of load, then torque is also proportional to square of speed. So then you can actually avail this kind of speed control techniques that where you can have some different operating points. But now, if you want to achieve at 500 RPM, you see that if it is like 6 Newton meter you want to achieve at 500 RPM, there is still no direct characteristics, right? If you see here, the same torque speed characteristics, you want to fit it here. These two are the feasible operating points. Either, and you will see that even if you go down the speed, if you reduce the voltage further, there is no feasible operating points, right? So you will see that these feasible operating points will be lying in this region only. You cannot reduce the speed to 500 RPM. So you don't have a smooth control over the speed. You have a very limited range of control over the speed if you want a very fixed torque kind of an application. Okay, so whatever torque it may be suitable for this fan kind of application, and that is what is been done in household application. If you have this fan or if you have the pump kind of system, you just directly go for a you see that the regulator which you use in your system, those kind of systems are actually applied. Right. So that is what is done. Now I will move ahead. Now the next thing is that you go for stator frequency control. Right. You can go for stator frequency control. That you recall that the expression for your stator frequency, that if you want to shift the synchronous speed by changing the synchronous speed also, you can change the frequency or change the speed of rotation. If you shift the synchronous speed, then you can do it by changing the frequency. Then also your speed will actually change. Now, if you neglect the stator impedance, then the voltage expression can be given by this. That is, this expression comes actually from the basic flux equation. And then if the voltage is equal to V rated, okay, Vs will be equal to Vs rated, then phi S will be equal to this expression, right? And you have the rated flux. Then what will happen if Vs is equal to Vs rated and you go reduce the value of frequency, right? This reduce the value to omega equal to actually omega is 2 pi f 2 pi of your supply frequency. So here, if you try to reduce the value of frequency, then you will see that if you see reduce the value of frequency, your flux will actually go. And suppose if it is going beyond the rated flux, that means suppose your flux is operating here. You keep your voltage constant and you increase the frequency. Then what is happening? You will see that the flux is actually going into the saturation region, which is not allowed. Okay. So only frequency control will result in saturation. And then since the saturation, if it occurs in saturation region, then the problem will be that it will draw huge magnetizing current, and induction motor, we know that the power factor is actually poor. So the power factor will even become poor if you try to go for simple frequency control. So that is why it is only simple frequency control is also not applicable. Now, therefore, you need to touch both. Okay, so variable voltage and variable frequency both. Then what is the best way to do it is that keeping the flux constant. Okay, we will see later on that why we try to keep the flux constant. Okay, so that is one important thing. So if we try to find out the expression of variation of voltage with frequency, okay, so This will be the variation of voltage with respect to frequency, trying to keep the flux constant. Okay, the flux expression is given by this. Okay, so basically, if we try to see from Vs divided by omega E, if we try to do the other expression, the other things will be equal to phi s into nph into kw divided by root 2. Okay, so here the thing is like nph and kw, these are basically winding parameters. So if you try to keep the ratio constant, then the flux will be remaining constant. Okay, so that is, it is expected that the flux will remain constant. And how do we try to control that? Up to base speed, up to the rated speed, it will be, flux will be made proportional to the speed. And after that, you above that speed, you will be uh, making it saturated at Vs rated. Okay, that is how you perform this task. So corresponding to this, have you will see the characteristic, this variation, the characteristics will be given by these expressions. Okay, you will see the characteristics. Yeah, the synchronous speed will also vary, and it will be able to, okay, you are able to satisfy the torque. You can actually vary the speed, and you can vary the torque. All these things, it is actually possible to do with the help of the motor. Now, here, if it is for fan type of load, both of them you are able to satisfy. But there is another problem. You see that still the maximum torque, suppose you want 500 RPM, 500 RPM and 20 Newton meter. Okay. So, or suppose 22 Newton meter. Okay. So at this position, you will be able to achieve 22 Newton meter, right? At this speed, you will be able to achieve 22 Newton meter. But below that speed, you will never be able to achieve. Why, we will investigate later, but now we have to achieve, right? We have to achieve at 500 RPM. I want to go for 22 Newton meter. That means at this point, I want to go to this point. Okay. I want to achieve 22 Newton meter. So how to do so? Okay. So corresponding to that, what we identify that in this maximum torque expression, there is one factor which will be the corresponding to the stator resistance. Okay, which actually is constant irrespective of the speed. Okay, so if you try to do at close to the rated speed, you will see that this factor plays a dominant role. Okay, but whenever the speed is zero, you will see that this will be the factor which will affect. Okay? So if the speed is zero, still this factor will be there. The stator resistance drop will be there. So corresponding to that, because it is a resistance can offer drop in a DC circuit also. So that means if you keep zero frequency, it will still consume some drop. That means you need to keep some voltage boost, which will actually help in overcoming the stator resistance drop during starting. And that is the profile which is actually inserted, right? This portion that we try to give this kind of a profile where the voltage versus frequency is given like this. Okay, the voltage versus speed profile is something like this. So such that, and at the rated speed, this will become zero. Before that, there will be some kind of voltage boost. Okay, some voltage boost, which this is the linear characteristics, and then some kind of shift will be there to compensate for the stator resistance drop. Okay, so this is given by here. Okay. Now, if you do so, then you need to, then by adjusting the voltage boost, you can actually uh, get some benefit out of it. Okay, so this will be the nature of the torque speed characteristics, and then you see that if you try to see or compare these two, that without the voltage boost, and with the voltage boost, you will see that at lower speeds also, your maximum torque is equal to the maximum torque at higher speed. But this adjustment in the voltage boost is somewhat ad hoc. Okay. So the drawback of this method, or what is called, firstly, what this is called actually voltage versus frequency, or variable voltage, variable frequency. This method is called, also called scalar control. So the scalar control will have a method drawback of stator resistance compensation. Okay. So you have to compensate for this voltage drop, and that if you try to do for the scalar control, it actually is an ad hoc basis. Okay. So that's why what we try to do, we try to go for what is called a vector control drive. Okay. So a variable voltage, variable frequency, but a vector control drive. Okay. So now we will start talking about the vector control. Before going into vector control, we will try to do a transformation of variables. Okay, so basically, if we talk about the drive system, the easiest and the most beautiful machine which actually gives the best performance is the DC drive system. Okay. DC drive system has the benefit that if we talk about DC drive system, you will see that the torque expression will be equal to, the torque is proportional to flux into current. It will be field flux and armature current. Basically, it will be proportional to field flux into armature current. Okay. The torque expression is given by, is proportional to field flux and armature current. Okay. So, and this field flux and armature, they are orthogonal to each other. That means they are at 90 degrees with respect to each other. So they don't affect each other. Okay. So now, can we, the essence of vector control is derived from this, that can we achieve, can we do some kind of transformation or some kind of control technique we adopt such that we can actually make the flux and the or the flux which is producing the torque and the torque producing component of current orthogonal to each other. Okay. So we have to actually, then it will decouple and then one will not affect the other. Okay. So that way we are trying to do. So before going into that, we need to go for the transformation of variables, which is given by this expression, that here any function, let us consider any function. This f can be either voltage, it can be current, it can be flux linkage. Okay. And this f is transformed to a fictitious reference plane, which is given by FQS, FTS, and F0S. Zero cannot be, zero sequence cannot be shown anyways. Okay. And this reference frame is actually a rotating frame. Okay. It is rotating with a speed which is given by, okay, this is given by this expression. Okay, omega e and then theta e. Yes, sorry, I could not. Okay. And this omega e is actually derivative of theta e with respect to time. Okay. So this is the expressions corresponding, and this transformation, and if can, this F matrix is given by FQS, FDS, F0S, And we have this axis corresponding to FAS, BS, PS and FCS, and we have these expressions. Okay, is called the parts transformation. Okay, so a transformation, and this transformation matrix is given. This is a transformation matrix. And this transformation matrix is given by this expression S equal to cos theta e. And these are the variables. This you can actually derive by doing some trigonometrical expressions. You can actually try to, you can get the hold of this function. Okay, so it is not a very big thing, but anyways you can do it. Right now, if we try to do the dynamic model, you can do it in two reference frame. One is a synchronously rotating reference frame. Another is what is called stationary reference frame. Stationary reference frame, this matrix you can just, instead of putting, uh, you just put, to derive the stationary reference frame, you just put S, substitute theta e equal to 0, then Ks will become S to indicate. You will see this one will become 1 minus half minus half. This will become 0, and this will be minus root over 3 by 2. This will be root over 3 by 2, and these are half, half, and half. I think that 2 by 3 is missing here. And this is called MMF invariant transformation. So here, uh, corresponding to this MMF invariant transformation, if we try to derive the stator voltage equations, that stator voltage equations will be given by this, where this is the applied voltage, this is current, and this sign is the flux linkage. This is corresponding to the alpha equation, this is corresponding to the beta equation. After that, you have the rotor voltage equations. Okay, so the rotor voltage equations will be given by this. That also transformation of the rotor circuit to the stationary reference frame, right? And that will be given by these expressions. This will be the stator flux linkage equations. Okay, this corresponds to the stator flux linkage equations. And this is corresponding to the alpha S, this is corresponding to the beta S, and these are the rotor flux linkage equations corresponding to the alpha beta frame. And this will be the torque equation. So this forms the dynamic model of the induction machine in the stationary reference frame. This will be the complete dynamic model of the induction machine in the stationary reference frame, right? And then you have the torque equation corresponding to this expression, okay? And here you can see this, this you can derive from this voltage relationship. And if it is squirrel cage motor or squirrel cage motor, the rotor is actually short circuited. This V alpha R and V beta R will be equal to 0. So this V alpha R and V beta R will become 0. So this will become actually, this will be nullified. Now you have the dynamic model of the induction machine. So if you see here, you will see that the stator voltage equations corresponding to these can be written also in the synchronously rotating reference frame. And this will be the stator voltage equations. And this will be the rotor voltage equation. So now, instead in the synchronously rotating reference frame, you see you have QS and you have Q axis, you have D axis. So this is my Q axis. This is my D axis. This is my A phase axis as well as my alpha axis as well, because theta is equal to 0. This is my beta axis. This is C phase axis. So these are the definition of the axis. Now, corresponding to the stator voltage equation, you have the QS component. This is the QS, and then you have this is the stator resistance drop, and you have the flux linkage, and this is the expression corresponding to the uh, induced EMF, which is omega E into psi ds. Okay, then you have the rotor voltage equation. So this is the complete mathematical model. This actually gives the slip frequency, which slip in angular frequency, which is induced on the rotor. Okay, so this is a physical explanation of this term. Then here also, since it is squirrel cage motor, let us consider squirrel cage motor. Actually, squirrel cage motors are only used in automotive application, and the slip rings are not. Squirrel cage motor, VQR equal to VDR, and that is equal to 0. And there you have the stator flux linkage also. This stator flux linkages, LS corresponds to the stator self inductance, LM equal to the mutual inductance here, and similarly this is done for the Q axis. Okay, and here there is one thing, there is leakage inductance also, that LS is equal to LLS plus LM, and LR equal to LS plus LM. Okay. So this leakage inductance is actually, this is leakage. Okay. And we have something called a leakage factor, which is given by sigma 1 minus LM square divided by LS into LR. Okay. So this is what is called a leakage factor. So this is given by 1 minus Lm squared into Ls by Lr. Right. Now, if we want to do what is called rotor flux oriented vector control drive, then under rotor flux oriented vector control, you will have this expression that psi dr equal to psi r. Okay, so all the component will be aligned to the rotor axis, and the q axis flux will be equal to 0. And then the dynamics of the rotor flux linkage will be given from this equation. If you substitute here, you just substitute PDR equal to 0, and psi QR will be also equal to 0, psi DR equal to psi R, and you substitute IDR using this expression. Okay, make it in terms of psi R, then you will be arrive at this equation. So this equation will determine the dynamics of the rotor flux linkage under rotor flux oriented vector control drive, right? And you see that the IDS will help you to control the flux. So if you, and at steady state, and you can use this expression as well to compute what is called sleep, and that is given by omega E minus omega R is equal to this, and there is tau R. Tau R actually refers to the rotor time constant, which is given by LR divided by RR. Okay, so this is the tau R. And then if you see the torque expression, yes, psi QR equal to 0. If you see from the torque expression that it is psi dr into IQS. So you substitute psi dr equal to LM into IDS, or you can put it psi R also. Now you have oriented the vector. So now it will be 3 by 2 P by 2 into LM square divided by LR into IDS into IQS. Okay, so this is the expression for your psi ds, or this is the expression for your torque. Now you see, in case of your DC machine, this actually you can represent by some K torque constant into IDS into IQS. Now, in case of your DC machine, this is TE. Okay, so this is TE in terms of some in the DC machine. This is for expression for induction machine. So TE DC machine, it is something some torque constant. Let me write as KT DC into IA into IF. Okay, or it can be expressed. So basically, this expression for torque will be analogous to your DC machine torque expression, where you have your IF is analogous to IDS and IQS will be the analogous to the armature current. And this has been shown here. Okay. So here you will see if you try to decouple between D and Q axis, this is my Q axis, this is Q axis, and this is D axis. If you go for rotor flux oriented control, then this will be the torque expression, and you can straight away control torque by means of IQS by and keeping IDS fixed. If you keep IDS fixed, your psi R will remain fixed and your Q axis will become the torque producing component, and you can just control torque by keeping psi R fixed. Okay. So this is a basic expression, and here you have psi F and you have your IF as well. So this is the analogy with the DC motor, that you will be able to achieve a DC motor like performance if you can go for the vector control drive. Now we will talk about two types of vector control. Now there are also two approaches to go for rotor flux oriented control. One is called the indirect field oriented control of induction machine. Other second one is the direct field oriented control. So in case of indirect field oriented control, you will have, this is a speed reference. After that, you compare it with actual speed, feed it to a PI controller. Then you have the expression for IQS reference and IQS, and then you give it to PI, and here you give some feed forward. I am coming to the feed forward expression. Give it to VQS, and then to perform DQ to ABC, because finally all your variables are in ABC domain, right? To perform a reverse transformation, and you try to send it to your all the to the inverter. Okay. So here this is, you try to and what you would like to sense. One is you would like to sense the speed. You would like to sense the two currents, IAS, IPS. Okay, then transform it to IQS and IDS. And if you are going for indirect vector control, then you will have to sense omega R, means basically you sense speed and then multiply with the whole pair factor. Then you will get the value of omega R, add omega SL to it, and then you will get what is the actual frequency. Okay, and you integrate it, you will get omega E. That is, and omega SL you will get from this expression. This is the expression corresponding to omega SL. Okay, so that is the vector control corresponding to your what is called the indirect vector control. Okay, so this is the indirect vector control. Okay, so this is called the indirect vector control drive. After that, there is another thing that you may not be willing to sense speed. Okay, without sensing speed, especially suppose if we want to do just torque control, then you can try to go for do the same thing by means of without sensing the speed as well. Okay, so you can go for torque control trades like here. Okay, it can be also applicable for speed sensing, but you can also do it for torque sensing as well. Okay, so here what you will be doing, that you want to go for directly, you try to get the position estimate directly from the flux. That is what is called direct flux or the direct field oriented control, right? So here, first of all, you try to get the reference values of alpha S and beta S, which is given from this expression. Okay, v alpha S and v beta S. Okay, and here you have the you sense I alpha. From here actually you get the values of currents, and corresponding to the value of current you can get the value of your I from IES IBS. You will get the value of I alpha S and I beta S by using the class transformation, that stationary reference frame transformation, right? So you will get these values, and from the reference voltages, you can then you apply what is called direct deposit technique. I will show you what is the direct deposit technique to get the value of theta e. Okay, so you will get the value of theta e, and the remaining thing is same, that the speed is controlled by the or for the speed controller will generate the IQS reference. ITS reference will be controlled to generate the flux within the machine, because it will create the flux, and you will try to keep it constant to keep the flux constant. Okay, so it is something like the field current control of the DC machine. So this portion is the field current control, and this portion corresponds to the armature current control and the speed control. Of course, is the speed control of the. Now, let us try to understand that how will we get the value of theta e. Okay, so from these expressions, how will we get the value of theta e? Now, from this figure, if we see that here, this is my, if we go back to this, this is my d axis, this is my beta axis. So we want to align, or we have to fix the d axis along the position of the rotor flux. The rotor flux is also a rotating vector, okay, because it is creating a, it is also rotating in synchronicity with the your stator field, and both of them should rotate at the same speed to produce effective torque. Otherwise, effective torque will not be produced. Okay, the average torque will not be produced. The average torque will become zero otherwise. So therefore, what we try to do, we try to actually align to the position of theta, or to align the d-axis to here. So you have to try to align the d-axis to this position. Okay. So to achieve that, what we will try to do, we will try to adopt first of all the voltage model for flux estimation. Okay, so from this figure, we have psi alpha r. Okay, so psi alpha r, and we have psi beta r. Now here, if we have psi alpha r, that is given by psi r into sine theta e. Okay, psi r into sine theta. Just apply the psi alpha r equal will be equal to the sine component of this theta e. Okay, so because we are trying to align to the d-axis, and psi beta r will be equal to psi r into cos theta i, psi r into cos theta i. And from that, we can find out this expression tan inverse of psi alpha r and psi beta r. Now, first question is, how will you get psi alpha r and psi beta r? Then only you can do that, implement the direct vector control. So, how to get psi beta, psi alpha r and psi beta r, that you can go from the flux linkage expression. So you have the reference values. Actually, this will be reference value p alpha star s minus rs into I alpha s and v beta s. Here also this will be reference value v alpha s into rs into I alpha s, and psi beta s will be there. And again, from the expression for psi alpha s and psi beta s, you will have you will use this leakage factor ls, and you will get the value of psi alpha r and psi beta r. Then take a tan inverse, you will get theta e. Okay. Now that problem with tan inverse is that is bit computationally not efficient. Okay, so this kind of trigonometrical expressions, if you try to use in your DSP based coding, it will take some more computation time. So it is a burden. Moreover, it is actually dependent upon this parameter RS. Okay, so RS varies. Then again, the compensation has to be put for RS. So that's why we don't prefer direct vector control. Okay, so the drawback of direct vector control is RS dependent. Then you need to either sense voltages. Now, if you have to sense voltages of a variable frequency drive, then it is a bit tricky, because you will have Actually there is if you have a variable frequency drive, then it is voltages are actually PWM voltages. It are square wave voltages which will be there. And if you have to try to find out the fundamental corresponding to that, then you have to go for some filtering techniques or something. So that's why the voltage, getting the voltage output from a VFD is not a very practical solution. Okay, so what we try to do, we try to use a reference voltage, but actually at lower speeds, the reference voltages may not be directly replicated by the VFD. Okay, because of daytime effect, because of the nonlinearity of the switches, there is some problem. Okay, so that's why what we try to do, that we try to avoid actually the direct vector control and try to rely on the current and the speed for implementing indirect vector control. Okay, there can be another way to do instead of doing voltage model for flux estimation, we can try to use, if you try to implement direct vector control, you can use what is called a current model to also implement, but that will also require the information of speed. Okay, so this voltage model uh, is actually RS dependent, and also reference voltages may not be replicated. Okay. So you can also use the take the help of what is called current model of flux estimation, where you have the rotor voltage equation. Okay, so this is given by this expression, and then you can also use the flux linkage expression to get what you call an expression where you can have a dynamic expression for, find it. This is a dynamic expression for psi alpha r, and psi beta r, which is given by this expression, and they are dependent on each other. Okay, and basically a simultaneous uh, non-linear equation, and simultaneous the differential equation which has to be solved to get these values of psi alpha r and psi beta. So this is also a bit computationally intensive. So if you try to instead of this, you try to adopt the indirect vector control. The indirect vector control is more simpler in terms of implementation, and that's why that can also actually help you to achieve what is, because finally if you try to sense speed in order to get this value of omega r, then again the problem is like then it can be easily, you can go for indirect vector control and try to actually do this and implement the system. Okay. So this is the drawback of the direct field oriented control. That is why it is preferable to go for indirect field oriented control. Okay. Now, next thing is the design of the current controllers. Okay. So we have used PI controller, and we told that we go back a bit. You see here, this is a PI controller, and this is a feed forward terms. Now, which is what will be the suitable control law? So that we will find out from the stator voltage equations, and that will help us to formulate the control law. Okay. So if we try to use the stator voltage equation, VQS equal to RS into IQS plus DIQS, using these equations, you consider that it is in rotor flux oriented control reference frame. So you go for psi ds equal to LS into IDS, and psi QS equal to sigma into LS into IQS. So what we will try to do, we will try to actually have an expression, and these expressions will help. If you substitute here, then you will get the expressions corresponding to the IQS and dynamic equations corresponding to IQS and VQS. So what you will try to do, this portion is corresponding to your IQS dynamics. Okay, here the IQS is different there, and VQS is my forcing function, right? At omega E into LS into IDS, this can be put as a feed forward term. this can be used as a feed forward term. Sorry, this will be my FFQ. Okay, so this will be my FFQ and this will be my FFD. So corresponding to this, these equations we will be using to formulate the PI controller. So here the control law is as follows: the PQS reference will be equal to PI into we apply a PI on the error, or error EIQS is nothing but IQS reference minus IQS. EIDS is given by IDS reference minus IDS. Okay. And then you give the feed forward control. The feed forward control will actually help you to achieve some dynamic, enhance the dynamic performance. Okay. So corresponding to a certain speed, if you, there is a certain jump, then it will give some voltage boost up itself such that the burden on the PI controller itself is reduced. Okay. So that is the effectiveness of the feed forward term. And now we try to see the current control loops. Okay. And if we adopt this here, if we see this current controller, IQS reference, you take the feedback from IQS, you apply a PI, you put the feed forward term FQS, and then you have the VQS reference, and minus your omega into LS into IDS actually will give you the transfer function. Okay. So if you try to go for the feed forward compensation, basically this will also give a complete decoupling control actually. So in that case, what will happen if you go for if we try to compare here, like VDS reference is equal to your VDS, then what will happen that RS into IDS plus LS into your DIDS dt minus omega E into sigma LS into IQS, that is actually equal to your this one PI controller over EIDS plus F into DS. Okay, so FFDS is equal to this one, so these two will cancel out. So finally, this P into EIDS will be equal to RS into IDS plus your LS into EIDS dt. Okay. So it is simple, right? So now you try to adopt. So basically, this is nothing but KP I plus KII by S into IQS reference minus IQS, that will be equal to RS plus S into LS into IDS. Okay. This is a D axis, right? So it will be D axis reference. Now, using this, we will try to do a pole zero cancellation, and you will come out. If you do a pole zero cancellation, then this will be the expression corresponding to the your D axis and the Q axis current controllers. Okay. And you try to adopt the same procedure for the Q axis, then you will be finding that this will be the current controllers for the Q axis reference. Okay. So that will be the control technique. Now, you see, whenever you are operating the drive system in your vehicle, you will have a limitation over the DC bus voltage, you will have limitation over the current as well. Okay, so the inverter can produce a certain amount of voltage, and the current is also will be limited by the thermal constants. So corresponding to that, you will have three operating modes in the torque split plane. One is called a constant torque region, another is called a field weakening region 1, the second is called field weakening region 2. Okay, so field weakening region 1, with only here only current constant is valid. Here both voltage and current constants are there, and here it is both voltage and only voltage constant will be there. Okay, so in the voltage and current equations, if you try to, this can be actually derived, and it can be shown that corresponding to the voltage limit, this actually forms an ellipse. Okay, so there will be certain kinds of voltage ellipse which will be there in the system, right? This is a voltage ellipse, right? And after that, you will see that with respect to speed, if you try to do it will be an ellipse because the major axis and the minor axis are different. Okay, so there is no concept of radius here, right? So here what will be happening, that, and this corresponding to this is the expression for the voltage ellipse. This is the expression for the current circle, current limit circle and voltage limit circle. These are actually shown here. Okay, so here correspond the voltage limit ellipse will actually go on shrinking with respect to speed. Okay, and then at one point of time it may happen that the limit ellipse will be going inside the current, and that is what is called the field weakening region 2. Okay, so now first of all what we will consider is the maximum torque per ampere. Okay, so maximum torque per ampere, the idea is that maximum torque per ampere with only current constant. Okay, under current constant, if there is no voltage constant, okay, that means you have infinite voltage, or it can happen that the voltage ellipse is always outside the current circle. Okay, so that this is at lower speeds. Oh, okay, at lower speed, suppose the voltage the ellipse will have a greater major axis and a minor axis, right? So it will be outside the current circle. And gradually, with respect to speed, it will increase when the speed increases, it will start going down. So what will happen now? uh, So what will happen? The torque equation in the rotor flux oriented vector control mode, if we try to see, we'll try to derive the expression for maximum torque per ampere control. So first thing, what we will try to do is that if we try to see the rotor flux oriented vector control, this will be the expression for torque, and under current constant, you see this expression is max and is t square. So is max square minus is t square. You substitute here because voltage constant is not there in the expression. So this is the one, and this will be the expression for the maximum torque. To get the maximum torque, this will, and then we try to solve for IDS and IQS. Once we find out IDS, you can take a derivative of this expression with respect to IDS and then solve it. If you try to solve it, the constants for current will be IDS equal to IQS equal to IS max by root 2. But it may happen that this will go above the rated value of IDS. So you try to limit it to IDS rated. So you try to limit it to IDS rated. Okay, and then that will form the MTPA line. Okay, now it may happen that the speed is increasing, your voltage limit circle with the voltage ellipse is actually decaying. Okay, so the voltage ellipse is decaying, and at one point of time the voltage limit or it starts to hit the current circle. Okay, so and it has interacted and it has hit the current circle at this position of A. Okay, so when the x-axis, that is the IDS axis, the x coordinate is equal to IDS rated, right? At this point, it has hit. Okay, so above this, you have to basically start field weakening. Okay, so because after this, the voltage will actually shrink further. Okay, so this point will never become, if we try to increase speed further, this will never become a feasible point. Okay, because the operating point has to be satisfied both by the current limit and the voltage limit. Okay, and here this PS max is actually it is rated or it is related to your DC bus voltage, input DC bus voltage by VDC by root 3. Okay, this will be the value of VS max. So now, if you cannot use it this ITS rated as a operating point, right? If that is the situation, then what I will do, I will have to reduce the value of IDS. How will I reduce? That reduction will happen, and that reduction is given by intersection of the point of the voltage circle. These are actually, this trajectory corresponds to the intersection point between the voltage circle, and all these points are lying on this portion are basically the intersection point between the voltage circle and the voltage ellipse and the current circle. Okay, so this will be the all these positions. Okay, now so for this equation, now this point, this point A, where the voltage circle actually, or the voltage ellipse meets the current circle, that point is called that speed corresponding to that point is the called the rated speed or the base speed. Okay, so this is the condition. So where the it is a condition where the ellipse intersects with the current limit circle and IDS cannot be increased further. Okay, so this point will be and then after that the IDS should be reduced, and the expression for base speed is given by this expression. Okay, that you can find out by using IDS equal to IDS rated and substituting that you can find out. Above this, if you have to find out the value of IDS, okay, so IDS MTPA you can obtain using this expression, and IQS MTPA still current constant is valid. Okay, so corresponding to that, you can actually adopt this to find out the value for the IQS MTPA. Okay, sorry, this will be IQS MTPA, not square. And once the voltage has actually shrinked and it has come down to the max point, suppose at this position, okay, at this position, this position, which is the point B, here this point B corresponds to a point where the voltage will actually, the voltage will limit, or the voltage limit ellipse will no longer be able to staying or below this, it will actually shrink within the your what is called MTPV. Okay, so at this point, you will see that MTPV will be actually prevailing, and this point B is called the point corresponding to the critical speed. Okay. And the for critical speed is given by this expression. Conditions for critical speed is given by this expression, and this is the condition for MTPV. The IDS for MTPV you can calculate using this expression. IQS for MTPV you can calculate using this expression. Okay. Now, for the overall speed range, suppose our rated speed is 1500 RPM, and then if we want to go for the overall speed, then what we will try to do, we will see that if we have the constant torque region, right? From the constant torque region, and then in field weakening region 1, on constant torque region, IDS is kept constant. Okay, so VDS squared plus VQS squared is less than this one. Here, IDS will become less than IDS rated. Okay, so IDS will actually decay. Okay, and there will be slight increase in IQS. Okay, slight increase in IQS will happen. Above that, VDS squared plus VQS squared, this will be equal to VS max squared. Here also this will be valid. Okay, and IDS will be equal to sigma times of IQS. Okay, so this will be the, and since current constant is no longer valid, it is defined by the voltage constant. So this will be the expression for IQS. Variation of IQS, this will be the variation of IDS. And if we see the torque speed region, okay, if we try to see the torque speed, so first of all, we will have the constant torque region. This is the constant torque region. After that, you have the field weakening region 1. Okay, so this will be the field weakening region 1. Then you have the field weakening region 2. Okay, so here the torque gives even further. Okay, and this is the constant torque region, and this typically is called the constant power region, and that has actually to this field region 1 where only MTPA with voltage constant. Okay, so here MTPA with current constant, with here MTPA with uh, voltage constant only. Okay, so these are the three regions of operation in the complete torque speed characteristics. Now we will try to find out. See, all it may always happen. It may not always happen that the machine is operating at the maximum torque. Okay, so corresponding to this operation. Okay, it may not happen that the machine is operating corresponding to the maximum torque. So suppose if you the machine is operating at any point here, okay, which is within the envelope of the torque speed, its torque speed capability. So we can do one thing which we can do is what is called efficiency optimized control. Okay, if it is not operating in the rated condition, we can go for what is called efficiency optimization or what is called loss minimization algorithm. Okay, so to do the loss minimization, we need to go for what is called that is called actually first of all we need to model the core losses also. Okay, so we need to do a mathematical modeling of the core loss. So here this mathematical model incorporates the core loss resistance which is given by RFE, and all others are actually there. Okay, so RS, you have the leakage inductance, you have the LM, and since this is done in stationary in synchronously rotating reference frame, so you have to take care of the IDS and SIDS and SIDR also. These expressions are there. LLR, RR, all these will be also there. IQMR, IQMS, all these things will be there. Then you have VDS. Okay, so this is corresponding to the D axis, and this is corresponding to the Q axis. Okay, and here psi QR equal to 0. Okay, so D axis is aligned with the rotor flux, and we are going for rotor flux oriented reference frame. Okay, so this actually circuit takes care of your rotor or basically the core losses. Okay, and we are considering the core losses is happening mostly on the stator. Major fraction is on the stator. The rotor is actually having either harmonic losses or it will be taking care of some minor losses because of the fundamental component, or it is which is referred to as your due to the slip frequency, right? Now you have the simplified equivalent circuit model to actually calculate the losses. Okay, so now what you will do here, you try to get the leakage inductance. Okay, so IQS, we neglect the leakage inductance. So this leakage inductances, LS, LLR, all these are actually, these are cancelled out. This is cancelled out. This is cancelled out. Okay, psi QS and psi QR equal to 0. Okay, psi QS, psi QR both are considered to be 0. Okay, and here uh, because leakage, if you this is corresponding to a rotor flux oriented, this IQS is corresponding to your uh, IQS equal to 0, because you are neglecting all the leakages, because IQS is nothing but sigma into LS into IQS. Now, if your sigma is 0, then IQS is definitely 0. Okay, so therefore, this D axis circuit, this IQS is 0, IQR is 0, there is no uh, and you will see that IDR will also become 0. Okay, so since IDR equal to 0, and here what is happening, IDMS will also become 0, because IDMS will be equal to IDS, because what will happen, the current through this will become 0, because here, since this is 0, the resistance and the inductor, they are becoming in parallel. So at steady state, these two will actually give you this, since this at steady state the voltage across the inductor is 0, so RFE, the current through RFE, the D axis current through RFE is actually 0. Okay, so that's why this will be the parameter corresponding to LF. Okay, so this will be the D axis circuit, this will be the Q axis circuit. Okay, so this will be the simplified equivalent circuit model. So this RS and IQS, IQMS, and this is omega E into LM into IDS. This portion will actually remain. Now you can find out what is IQMS. IQMS will be given by, just try to solve the circuit. You will get the equation for IQMS, and that will help you to calculate the losses. You can go for the stator copper loss by finding out IDS square plus IQS square. IDS is actually equal to IDS, whatever means whatever IDS you are stating, and IQR, and the rotor copper loss is RS into IQR. Okay, and that exact IQR and IMR will be equal to IQR and IQMR will be actually same. So and that equal to minus IQMS, because your IQR equal to 0. So that's why you can find out IQMS, and then after that from IQMS you can find out IQMR, and you can find out IQR, and you can calculate the rotor copper loss. So this will be the total copper loss, and then the whole loss will be equal to the loss in this resistance, and that loss in the resistance is given by your I loss in the resistance is given by this expression RAP into IQS minus IQMS whole square. Okay, so if we try to substitute here and try to take out we substitute everything here, and then try to actually derive the expression for PAP. You try to put the expression for IQMS in this here, then you will find out the expression for the value of your PAP will be obtained, and then the total losses are given by this. Now, if we have to minimize this total loss with respect to IDS, okay, so you can try to, because IDS now, IDS and IQS will try to find out a relationship with respect to somewhat an omega E. So we'll try to differentiate this with respect to, for a particular value of torque, how much IDS will be actually required. Okay, so if we have to try to find out, then we can find out this expression that ITS will be equal to the what is called the efficiency optimization criteria, and this K mean, or the minimum loss minimization factor, which is called, this is given by this expression. Okay, so this is the loss minimization factor, and you try to adjust the magnetizing current. The idea is like that at lower values, if you see that lower values of torque, you will, the cold loss actually becomes the dominant factor. Okay, so since cold loss becomes a dominant factor, so it is try to minimize the cold loss. Okay, the copper loss is actually reduced because your current will be reduced. So at lower values of torque, the since current is reduced, your copper loss will actually be reduced. Okay, so corresponding to that, you will have then corresponding to that, your If you try to reduce a cold loss by reducing the magnetizing current, then your flux will reduce and your overall cold loss will actually try to reduce. Okay, so here the algorithm dynamically maintains the optimum balance between copper and iron losses. So it can be implemented in field-oriented control as a loss minimization algorithms, and this is a loss minimization factor which is dependent on machine speed and parameter. Okay. But actually, this is dependent on machine speed and parameters. So there are certain search-based algorithms which actually takes care of the loss minimization. But you can also go for loss minimization based on the parameter model or the model-based loss minimization controller, which is given by this expression. So we try to summarize the overall topics which have been discussed in this. So scalar control is simple in terms of the implementation aspect. Then vector control will be, because scalar control, you will see that it doesn't require much amount of sensor. It is an open loop type of control. Okay, so just voltage and frequency you need to vary. There is no vector transformation. There is no transformation of variables. The tuning of the controller is simple. Okay, so you can do it on a trial and error basis. So the scalar control is a simple in terms of implementation. Okay. And then if we talk about your vector control will give you improved time and steady state performance, but it will require more number of sensors. Like it will require at least two current sensor. It will require at least one speed sensor for implementation, right? So these two will is definite. Okay. So vector control, but it will improve the dynamic performance as well as the steady state performance. It is easy to implement a maximum torque per ampere control using the vector controller, right? And then you can go for a defined methods of realization of the vector control. Either you can use a direct vector control where you can be able to eliminate the dependency on your dependency on the speed sensor, but you will be able to minimize the resources, but the control accuracy may not be that achieved because your stator resistance, it is dependent on stator resistance. There is problems related to the voltage. Okay, so all these problems will be actually there. So defined methods of realization of the vector control can be in that respect, indirect vector control, especially for starting performance, especially for the low speed operation, is a better algorithm. Okay, so the indirect vector control forms a bit major advantage. Then to utilize the machine in a better manner with respect to your voltage and current. So we go for maximum torque per ampere control, which is for RMS current minimization. Based on the voltage constraint, you have the maximum torque per voltage control. Now, here actually you go for maximum torque per ampere control in below the base speed. In the starting performance is governed by the maximum torque per ampere control. Then you go for uh, second field weakening region. Actually, the torque speed characteristics will have three modes of operation. One is the field weakening region one is the field weakening region 2, and then the below base speed or the constant torque region. So these three regions will follow the maximum torque per ampere control for the RMS current minimization. Okay, so that actually will be helping in the effective utilization over the whole torque speed characteristics, right? So that's why this maximum torque per ampere control, maximum torque per voltage control implementation of this has become an important aspect, especially for the automotive application. Then suppose when you are trying to put it on the vehicle, then there will be a battery which will be actually discharged when in the motoring board. How to prevent the battery to get le- less discharge or the depth of reduce the depth of discharge of the battery? That will actually help you to reduce the range anxiety of the vehicle, right? So you try to adopt a loss minimization algorithm, whatever machine you designed. Okay, So now, okay, your machine is optimally designed. The machine is the efficiency as high as possible you have achieved, right? Now you try to from the control algorithm itself over the different operating, you have the different drive cycles like US06, you have UDDS drive cycle. Corresponding to that drive cycle, you have loss minimization algorithms. So where you can actually help you to reduce the amount of energy obtained or the amount of energy consumed from the battery. Okay, so that will be another effective method. Okay, so these references you can use like for the initial part of the lecture where we talked about the modeling the induction machines. So you can use this for the modeling of the induction machines part and the steady state and the dynamic model. Then you can follow the Leonard for your vector control. Then you can go for the loss minimization algorithms. You can refer to these papers for the loss minimization algorithms. And you can refer to the paper by Professor S.K. Sool for the MTPA and MTPV to understand the field weakening operation of the induction machine. Then you can also refer to this paper for constant MTPA criterion. And also you can refer to this paper for stator resistance estimation in induction motor drives. Okay. So thank you for your patient hearing. Now I am open for questions.
Uh, Thank you, sir, for your
Yeah,
lecture. So,
thank you for your patient hearing.
any queries from our participants, side? Any queries? Please let us know.
Yes, yes, please. You can put your questions here. No.
Okay, I think there is no queries from that participants.
Okay.
I think so. So, thank you, sir, for
No,
your great.
then I will continue
Hello.
with
Yes,
something
yes,
more.
yes. Hello.
So what actually just I would like to inform you all to the participants about the structure of IIT Delhi and that like about CART means Center for Automotive Research and Tribology. So few minutes I would be talking more
Sure,
about
sir.
this.
You please take your time.
Yes, yes. So since time is there, so I think we can continue a bit. Like see, if we talk about the there at in IIT Delhi, what is the structure is like we have departments, we have centers, we have schools and center of excellence. Okay. Now, departments are basically, if we talk about departments, so departments like electrical engineering department, chemical engineering department, then civil engineering, mechanical engineering, we have the different departments. So departments will have UG teaching, okay, and centers on the UG and PG, and they will also participate in research. So centers will have a definite thematic area, right? Thematic area based on which, suppose we have different centers like Center of Atmospheric Science, Center for Biomedical, and CART means Center for Automotive Research and Tribology. CART, where I belong, is a center. Okay, so center where only we are more focused on PG teaching. Okay, we conduct master's program and uh, we have master's program and we have uh, PhD program as well. Okay, so both masters and PhD we offer. Masters means we have MTech program, regular MTech, part-time MTech, full-time sponsored MTech, and we also have full-time Masters of Science by Research. Okay, where Master of MTech program is actually the program where you have more course-based things. Okay, so you have some course activities which are there. Okay, so here there are you have to conduct courses, you have conduct laboratory, and then there is a project. And if you are going for MSR degree, then the number of courses will be less. Okay. And here your number of courses will be less. And it is MSR means it will be more research focused, means from the day one itself, you will be oriented towards a particular problem or a particular direction of research, and you will be taking up courses related to that area of research. You will not be taking up all the generalized courses or all the mandatory courses, or courses are basically optional to you. Okay. So all these things will be there. So that is the two modes of mm, or the two modes you can do for PG, and you will have PhD. So you can go for PhD, which is like after BTech also, but BTech if you after BTech if you go, then you must have 8 point CGPA, and also you have to contact take more courses, undertake more courses. And if you go for PhD after master's degree, then the number of course credit requirement is less, and your it will be more focused on uh, research, and you have to undertake less number of courses. Okay. So this is the overall structure of card. Now in our center or in our motor design lab, we have different facilities and more activities which are there. Right, we are currently working, since it is motor design and drives kind of laboratory, so we have uh, projects related to multi-phase induction motor drive, where we are trying to increase the regenerative braking efficiency and try to reduce the overall consumption of the consumption on the multi-phase induction motor drives. Okay, so these are the different topics we have, and then there we have development of reduced rare earth interior permanent synchronous machine. So this we actually have with collaboration with one industry, and we developed this project. The project was funded by METI. So here what we did was that we developed the 5 kilowatt, which is a laboratory scale prototype in our lab. We tested it in our lab. After that, the upscale version was done with the help of the company, which is Suyo Manufacturing India Limited. So Suyo Manufacturing Private Limited, who actually helped us to upscale the design from 5 kilowatt to 30 kilowatt. Then we are currently looking for development of synchronous reluctance motor. We developed one prototype with the help of one industry, which is Cast 10X India Limited. And here there was where we actually talked about the performance analysis and the design of a synchronous reluctance motor, where there are no magnets. Okay, so in such machine, there is no position of any magnet. Okay, and you can go for it is a rear arc free motor. Induction motor also is a rear arc free motor, because now there is a thrust to go for rear arc free technology. So that's why there is an thrust to enhance or to improve the performance by means of uh, this kind of structure. Okay, so that is what the rotor structure they try to modify. We have designed this one. It is currently under testing phase. A 7.5 kilowatt synchronous reluctance motor has been actually built. Then there is we are also working on integrated charger, where we try to go for the filter inductances of the charger is realized by with the help of the motor winding inductance. So that is called the integrated charger. Okay, so where we try to reutilize a portion of the powertrain and use it for charging the vehicle as well. Okay, so that is somewhat a utilization problem, and we successfully developed one phase of the this we developed one prototype in the lab. We are currently testing it, okay, and we are working it for, and we are looking forward for to work on the three-phase integrated chargers for the different other category of vehicles, not for two-wheelers definitely. And we are also working on six-phase interior permanent magnet motor, okay, where we are trying to compare the different windings topologies for the six-phase interior permanent magnet motor. And we are looking forward to work on development of motors for drones, okay, like axial flux kind of motors, reduced rear earth axial flux motors, or rear earth free axial flux motors. So we are thinking of different topologies or different types of motor development for drone architecture, because drone technology is coming up in a big manner. So that's why we are thinking of developing those. So if some of you are interested, if you can, you are interested for applying for masters, MSR, or PhD, the application deadline is unfortunately today. So you please, if you would like to apply, you please go ahead and apply. Now we have different projects also in the laboratory, like we are having the development of high efficiency motors and controllers. Like I had talked about, our lab was mostly focused on the development of 30 kilowatt IPMSM, a 5 kilowatt IPMSM, which was upscaled to 30 kilowatt IPMSM. And it was with the funding from received from Ministry of Electronics and Information Technology, with the help of which we developed this prototype. Okay, so we have successfully tested the 5 kilowatt prototype and we found the results. Now it is it is in results reporting phase and we are about to close the project. Then we had a project with CIZ, and here we tried to develop some. Which it is not a developmental project. It is something like knowledge dissemination kind of things, where we talked more different charging methodologies for this purpose. Then we had project with, I was one of the co-PIs in this project. So development of new drive topologies, which was funded as a startup grant from IIT Delhi itself. So with the help of which we developed some initial topologies for the integrated charger, as well as we developed some initial topologies for the induction motor drive as well. After that, we have developed, we are in the development phase. We are in touch with Sona Comstar, uh, BLW. Their team we are working with for the development of rotary transformer for electrically excited synchronous motors. Okay, so basically this is also to reduce the content of rare earth magnet and also go for electrically excited machines, where you have the brushed motor. Instead of the brushed motor, brushed electrically excited synchronous machine, you can have alternative, which is the induction motor, or not an induction motor. It will have the electrically excited synchronous machine, a brushless topology, which you can do by means of the rotary transformer technology. Okay, so that actually will be helpful for the rotary transformer. Then uh, I had already mentioned that with the help of Castanex, we are developing the Tijbras lactase motor. Then it was funded by Horiba, and we developed some prototype of IPMSM bit to reduce the rear earth content of interior permanent magnet synchronous machine. So we tried to use certain uh, content of the rear earth we were trying to reduce by help of certain design modifications. So we did the design in analytical design, did some simulations on JMAC, went for the prototyping with help of local manufacturers. So for that, we had some fundings opportunities and we got it from the CSR fund. Now, currently in CART, we have a center of excellence which is being developed parallelly. That is Hyundai COE, which is Hyundai from Hyundai. It has Hyundai Korean Motor Company. It has been developed, and so we are looking forward for some students and collaborations also for the induction motor topologies. Okay, so to who are interested to work with uh, on the induction motor drives are welcome and to join our lab, and we will be floating advertisements soon. We and we have opportunities for PhD students as well. So moving ahead, we are in talk with Tata Motors as well, and we are in talk with Hyundai Motor Company for an extension of this project, where we are thinking of integrating AI and ML content in the control of induction motor drives. So this is the brief overview of the lab, and great thank you to all of you. So now if you have further questions on this topic as was in this portion as well, you can please go ahead.
Sir, one question they have asked. Okay, one.
Yes, 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 please, please, please.
Yes,
Sir, good
the question is why rotor flux oriented FOC is popular compared to stator flux slash air gap flux based FOC. Sorry, it is compared. Okay. Why rotor flux oriented FOC is
I've got
popular
the question.
compared to stator flux slash air gap flux based FOC?
Okay, so yeah, this is good question. Like if you go for stator flux or your air gap flux kind of thing, then actually you will not be able to achieve decoupled control over the torque and the flux. Okay, so the DC machine like performance you will not be able to achieve. Okay, so unless you make, if you see refer to this torque equation, you see that if you go for this one, then it will not, if you see this, if you don't make psi qr equal to 0, then it will happen that your uh, if you don't make psi qr equal to 0, then your torque expression will not come in this form, which is not in the form of a DC machine. So this torque expression, if you want to make it in the form of a DC machine, then you have to make psi qr equal to 0, which indicates that your rotor flux oriented control is there. Okay, so and if you want to go for stator flux oriented control, also it is possible, but then also you have to use a decoupling factor, which has to be introduced in order to go for stator flux orientation. Indeed, it is a good question.
So good afternoon. Shall I ask my query? Am I
Yes, yes,
audible?
please go ahead. Yes, yes, you are audible.
So
Yes, ma'am.
actually,
Yeah,
this
yeah.
is Sheila. Myself, Sheila, research scholar from Chennai, Tamil Nadu, actually, sir. I could see some
Yeah.
projects under EV and also my area of interest is
Hmm.
EV. If I want
Right.
to get equipped with these things, how could I contact this cart and also what should I do for this? I could see some projects with EV like design and development of electrically excited machines, and I was have taken a big
Hmm.
development of new drive topologies for EVs and all. If I have to
Right.
if I have to join, if I have to learn something from these things, what should I do actually? Can you please guide me in this, sir? That would be very helpful for
Acha,
me.
now one thing is that see these projects actually, if you were to like to join this project, then you have to apply in a full-time mode. Means since you are already employed, and also
Okay.
you can come for internship kind of thing, or you can come as a visiting scholar here. Okay, so
Oh, thanks,
or as
sir.
a visiting scholar, so you can directly apply to me, or yeah, that is the easiest way to go for.
So I can take your mail ID, right? I have seen it in the website. I have taken your mail ID. Shall I mail you then regarding this,
Yes,
sir?
you can mail me. You can mail me. You can mail me.
Thank you so much. Thank you so much, sir. Thanks a lot. Thank you.
Welcome. Welcome.
So, any other queries?
Do we get the slides
Hmm.
for this talk? The talk is really excellent. Can we have the slides or uh, recorded mode or something like that? Hello.
Yes, I
Yes,
think
you're
Professor,
audible.
yes,
Yes,
I
can we
think
get
Professor Ghosh can,
yeah, PPT or
Arnav sir can, I think, respond better. I can send it to Professor Ghosh.
okay, thank you.
Haha, hello. What's your query? Please tell me again.
Do we get the PPT or the
Yes,
presentation?
yes. I'll ask sir, then I'll share. Okay.
Great.
Okay,
Really
okay.
excellent lecture. Thank you very much.
Thank you.
Yes.
Thank you.
Okay, so any other queries? Okay, I think there is no query, sir. And your
Okay, okay. Thank you.
presentation
Thank
is
you.
very good. You have started from very scratch level to up to that real-time application. So it's really nice and very good. Okay, so I hope that participants are able to understand a lot of things from here only, your presentation. So thank you, sir, for giving us your valuable time and deliver the nice presentations. Okay, thank you.
Thank you. Thank you. Thank you for giving me the opportunity. And we look forward and we welcome all of you to CART IIT Delhi. And definitely we have different projects. We have industry collaborations. So we have laboratory setups. So you are welcome to visit us and have a look. And if you are interested, any of you are interested to pursue further studies in terms of PhD or masters. I don't know whether BTech students, bachelor students are there. So you are welcome to do so. Okay. Thank you.
Okay, thank you, sir.
Thank
Thank
you.
you.
Thank you. Fine. Thank you.
Okay, so we are going
Okay.
to conclude our current session. Okay, so next session will be from 3 p.m. onwards. Okay, we'll join after the lunch. Okay,
Okay. Thank you.
thank you.
Teachers like